Okay, we're live. So today we're looking at more patterns. And we have two kinds of patterns in this unit. Today we're going to be looking at patterns which are a little bit different than we looked at yesterday. Yesterday we looked at patterns mainly that added or subtracted, and the first day we looked at a combination of different kinds of patterns. So today we're going to look at patterns that I don't think they add or subtract for each step. So how about we look at this dots pattern first. So what do you guys see is going on first? Maybe we should write down how many dots there are and then we'll talk about what's going on. You already know?
It's doubling. It is times 2.
It's times 2, it's doubling, nice. Let's make sure, let's write down how many dots and confirm that, shall we? How many dots are there day 1?
6.
6, that's pretty easy. And at day 2?
12.
12, you could look at that as like 2 packets of the original 6, right? So that's the doubling feature that we see. Good. And then if we double that, we could try to count all those dots. But if we're pretty sure, I mean, this is already going to be 24. Cool. So we don't know what the next picture looks like. I didn't want to draw it. You don't want to draw it because that'd be a lot of dots, right?
It'd be 48 dots.
It'd be 48 dots. How about if you were asked about day 5?
It's double 48.
48 times 2.
Do you have a calculator? Somewhere. So find it.
I'm looking. That's not it.
96.
96 is the next day. So you could keep doubling like that forever. So there's 2 ways to write this down, I think. We've got one way that's recursive, and we've got one way that's explicit. So that's what we're going to be looking at today, is patterns that do things like double, for instance. How do you write them down in a couple different ways? You can write f of x, you can write y, you can even write them in other notations. We're going to focus mainly on y and f of x, since that's what we started looking at earlier. So you guys said it was doubling. I think that's the way that you want to do recursive. That's the easiest way to do recursive. And I'm not even going to do it real symbolically. I'm just going to say now equals what you had before. In other words, you can say that different ways, but the previous term. And what do you do with that previous term to get what you have now? Multiply it by 2. Exactly. So you can put more symbols on there, but that's how you want to start thinking about these. Explicitly, this might be a little bit harder for us to think about. So we have a multiplying by 2 in there somewhere, though, right? So if you think back to your handout, you're going to be multiplying by 2 once, or twice, or 3 times, or 4 times. It could be however many times multiples of 2, right? Well, how do you write that with an x? You write that as 2 to the x power. For this example, x would be what? How many 2's? It'd be 4. For that example, it'd be x is 3. For that example, it'd be x is 2. So that's 2 to the x power. So let's check and see if that's good enough to get what we have up here in our pattern. Is that the equation? Is that the explicit equation for the pattern? If we plug in 3, what are we supposed to get? So if you plug in 3 right here, what's 2 cubed? You could use your calculator, but that's a number you should be able to do in your head. 2 times 2 is 4, times 2 is 8. It's supposed to be 24. Crap. Not correct yet, so I need to add something else to fix this up. I think we want to add or multiply something, but this kind of sequence is all about multiplying. You guys told me at the beginning it was doubling, it was multiplying, everything in here is multiplication.
2 times 2 to the
You have it, Miss Bradford?
3.
Times 3? Let's see. So if we put 3 in, you can check it with any of these, right? But if we put 3 in, we're supposed to get 24. If we put 3 in, that's 8. 8 times 3 is 24. How'd she get 3? How did you get 3? You divided 24 by 8? She divided it by 8.
Yeah.
So that was a smart way to do it. You could also see it in the pattern. Or guys, remember, we talked about it 3 times now.
Oh.
If you go back to day 0, you can kind of see the starting point. So if that was day 1, what would it have been at day 0? There's all kinds of different ways to do this, but if that was 12 and this is 6, then this would have been 3, right? Wouldn't we have had 3 dots like that for the very first step in the pattern? So that would have been 3 dots, and that's this 3 which Miss Bradford came up with a different way. She came up with it by modifying the 2 to the x. Those are both good ways to come up with it. That's the explicit. So these are both good ways to think. If you want the 6th term, you could just, keep multiplying by 2. What if I asked you for the 108th term?
Okay, you would have to go with the explicit because that would be like crazy.
It would take forever, and you might lose track of where you're at, right? It'd be really easy to lose track. But for the explicit, it'd be really easy to find the 108th term. You just plug in 108, and you can use your calculator to do it. So why don't you guys use your calculator and tell me, what is y? And you know what, let's write it like this, y sub 108. That's the 108th term. So we're going to say that. So you guys tell me, I bet it's a huge number. It might even overflow your calculator. Your calculator might not have enough memory. So you guys tell me if your calculator can do it.
It's like, I don't know if that works. Did I put it in?
Does it have an E in the end?
Yeah.
Yeah, then you did it right.
Well, it's E32.
Mine doesn't have it.
So what's that mean? That's something else we need to talk about today, because you might see it.
Yeah, mine's
9.735556661E32.
So it's something like that, right? What's that E mean? That's scientific notation, which we're also going to learn this year thoroughly at some point. So here's your first experience with scientific notation. That means times 10 to the 32 power. That means there's 32 zeros after this 9. It's a gigantic number.
Oh yeah, I remember.
And that should make sense. If we go out 108 days later, this group of dots is going to get bigger and bigger and bigger. How much bigger? Unimaginably bigger, pretty much, right?
Probably that entire way.
Oh, more than that. Good question, though. I think it would cover like the entire county of Pueblo, actually, if you tried to draw all those dots. That's how unimaginably huge that number is.
We should do that.
So let's do it with one more. So here's another pattern, different pattern. Let me erase this guy. Let's talk about this pattern.
We would not go to 8 now.
Okay, so first step, let's just write down what we've got. And then we'll try to fill in the next couple ones.
Are you? Yes.
So, how many triangles?
1,
Boring. How many triangles?
3, no 4.
4.
3. Oh.
How many triangles? Might have to be more
16.
careful. Is it 16?
Yeah, I'm pretty sure.
7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And Andrew is correct.
Woo!
So what's happening here? I think the pattern's a little bit harder to see.
It's just adding another line of triangles on the outside.
No.
Times 4.
Yeah, it's just circling the triangle on the inside with 4 triangles on the outside.
And you said
Times 4.
times 4, and you're talking about the visual. Those are both good, right? Those are the kinds of things you want to talk about when you're doing your own problems. Very good. So what will we get for figure 4 without drawing the crazy triangles? That'd be really hard.
64.
You've got your calculator. And what would you get for figure 5? How many triangles?
We should draw that too.
Yeah, that'd be rough. Okay, so let's talk about what these would look like recursively and explicitly. So recursively, and I'm not really giving you the full version of recursive yet. I'm trying to make it a little easier to understand, not a lot of symbols. So that's the one where you count, right? It's the counting one. So that's going to have like now equals the previous term
Times 4 by 4.
times 4. Exactly, that's all there is to it for that, right? For explicit, can you guys help me this time a little more?
Y equals 4x.
4x like this?
No. Well,
So that's when you're adding something lots of times. We're not adding something lots of times.
Oh, dude, we're 4 to the x power.
We're multiplying lots of times. This is how you say multiplying lots of times. 4 times x is how you say adding lots of times, because it's that many x's. This is 4 times 4 times 4 times 4, however many 4s you need. Yeah, you can use my book. Yeah. Okay, so is that going to work? Let's try it. If if we plug in 3, what are we supposed to get? Try it, plug in 3. What's 4 cubed in your
64.
calculator? Well, but it was supposed to be 16. Poop. So how do I make it be 16? I could maybe subtract something.
4 to the second.
I could maybe divide something.
What
What goes better with multiplication, division or subtraction?
Division.
Division, and isn't that what Miss Bradford said a second ago?
Oh, you're gonna divide by 2, right?
64 divided by 2, is that 16?
No.
Divided by 4.
There we go, yes, very good. So you could go like
Hey,
this.
You said the multiples are correct.
That'd be correct. Another way to write that, which I think you'll see in your problems more often, is 1/4 times 4 to the x. Either thing is plenty good. That's how you write down that guy explicitly. Now, it's going to be a while before I test you on coming up with a sequence like this. This is a little bit tough. We're going to practice a few times, but we're going to take our first exit quiz tomorrow.
Alright, how are that?
But I'm not going to expect you to do something like that one exactly yet. You know what I mean? So I'll be giving you them. Yeah.
Wait, isn't 4 times 3?
What are you talking about?
Never mind.
Let's look at a couple more examples where they kind of just give us these and we make a decision. Okay, so a couple more examples.
I don't like making decisions.
We all know
Add a couple more things. So we'll do 2 more. So our third example. Let's say they give us this information.
Because she had to make 2 cul-de-sacs. Is she here today? Bro, that'd be everywhere. You know.
You guys want to get these down? If you come to me later and you're like, I don't know what I'm doing, Mr. McGee. And I'm like, okay, where are your notes? And you're like, oh, I didn't think I needed to have them. I'm going to be like, well, bad decision.
Not everything. Where you can, like, if you break something, just YouTube how to fix it. Right? Yeah. Until it comes to, like, glass plates. And it's just, like, duct tape and super glue. No, bro. You want to get, like, the cheap super glue. It works better. It really does. I don't know. Yeah, it does. It's always so much cheaper.
Okay. These are very similar to the ones I gave you. So, same situation, except I didn't show you what the pattern was. In fact, I didn't even give you a table. I just gave you the forms of these sequences.
It's just plugging numbers in, right?
Kind of, yeah. But you got to make a decision. So, there's some new notation here. I would write it down in your notes for yourself. This is pronounced the 12th term in the sequence, or a sub 12. So we have the explicit version of the sequence, or the equation. We have the recursive version of the sequence, or the equation. And we know about one spot, just one spot. It's like a starting spot, okay? So this is the 12th spot in the table if we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool? So, if they ask us to find, what is this then? The 13th spot, exactly. Very good, Hunter. It's the 13th term in the sequence. What would be easier to use? Would the explicit or the recursive be easier to use to find the 13th spot?
Explicit. Recursive.
I mean, you can use them both, sure. But you want to pick the most efficient one, and that's how I want you to do your problems this time. So recursive is definitely the way to go on this problem. Because how far is it to count from 12 to 13?
1 point.
Our recursive for this one says now, what you want when you're 13 is what you had a second ago at 12 plus 8. So what is this going to be then?
13. No, whatever, yeah.
The thing we had a second ago was the 12th. We're at 13.
I get it.
Now we're 13. The thing before it, the previous term was the 12th one. Add 8, you get 100.
Oh, wow.
okay.
I'm literally.
Wow.
No, you're fine.
No, I
Fine, no judgment.
Something. No, I'm judging
Okay.
myself.
You guys get it? But see, if we have to compute the 80th term, we could keep adding 8s, right?
Oh my gosh.
That would take a long time. It'd be easy to lose track. This is where you want to use your explicit one, because it's much farther away. And I'm going to ask you to explain on these, so you need to talk about whether it's close, whether it's far away, something like that. So the 80th term, instead of going plus 8, plus 8, plus 8, plus 8, plus 8 from 12,
So just do the explicit version.
I'm just going to take 80 and put it
Into the explicit.
into the explicit. Yeah. So I'm going to get
So-
8 times 80
Problem.
Minus 4.
No,
minus 4, and I'm going to use my calculator. Did you do it already?
Like 640 minus 4.
So this is 640. Why don't you guys check that?
636.
It's 636.
What I got.
Yeah.
Minus 4.
So 632.
There we go.
I put 8 times 80 minus 4 and I got 636. So.
So if
Oh.
I get like a bigger problem, I'm doing
8 times 80. Let me double check. 8 times 80.
640.
This is 640.
Yeah, the answer is 636.
Yeah, okay. Thanks, guys. Okay, so now you guys help me with this one. You've got another explicit, you've got another recursive, you've got another starting spot. This time we're starting at the 3rd spot, and it's 108 there. So if we want to find the 7th spot, which one's better to use?
Explicit.
You think explicit? Yeah, it's a little bit far away from 3. We could probably count it, but yeah, it's not right next door, right? So let's go with Jeremy. He wants to use explicit. Let's do it.
Yeah.
So we're going to go, it's equal to 4 times 3 to the 7th power. So that's going to be 4 times what? Can you guys tell me what's 3 to the 7th power? It's going to be a big number, I bet.
8,748. Oh, wait, no, that's the answer that I got for the whole equation.
You guys confirm, Jeremy. You should be doing this at the same time just to make sure you know how to do it.
3 to the 7th power is 2,187.
Yeah, Miss Bradford confirmed you, thanks. Okay, and then that times 4 is going to be
8748.
sweet. We didn't need our calculator no matter what here, right? If we were multiplying by 3, it would have been pretty big, pretty fast.
Oh, wow.
So I think that was a good choice, Jeremy. Very nice. If we want to just find the 4th term, though,
That's what I did.
and we've got the 3rd one,
Just the recursive,
Oh,
just
then
multiply that
just
by 3, which is...
just take the previous one, 108, and multiply times 3,
Yeah, no, I did that wrong.
and you'll get, I think, 324.
Yeah. I keep trying to multiply like the 3 times the third,
Ooh.
the third,
Yeah?
the
A2, I was just thinking.
third.
So A2 is the challenge question. How do you get A2? So we have A3, we have A4 now.
You divide by 3. Divide 108 by 3.
Very good, very good. I was wondering if that goes through you guys. You divide the 3rd term. To go
36.
backwards, you divide.
So
36.
There we go. If I asked you for the 1st term, divide again, and you'd get 12. If I asked you for the 0 term, you'd divide again. And 12 divided by 3 is
4.
there's that. So this stuff all works together. The recursive, the explicit, it's all the same stuff. It's just different tools that you have. I'll see you next time.
I have